Hello everyone. Today I will be walking you through the part A of assignment process of determining the point group of a unique crystal structure. Specifically, we focus on identifying the point group of the crystal given in the class. Here, this is the crystal structure provided in the class. We will discuss the point group of this crystal structure. First, I will be giving the brief introduction about the symmetry and the point group. The crystal structures refers to a set of operations like rotation, reflections, and inversions that maps the crystal structure onto itself, making it appear unchanged. These operations defines a crystal internal order, categorizing the specific point group and crystal structure. So I will talking about the importance of the point group. So point group of the crystal is a classification based on its symmetry elements, which plays a vital role in understanding the crystal's physical properties, classification, and behavior. Symmetries affect the optical and electrical magnetic properties. For example, certain point groups allow phenomena like piezoelectricity, while others do not. Point group also helps classify the crystal into systems like cubic, tetragonal with the shared characteristics. Additionally, point group symmetry simplifies the interpretation of X-ray and electron diffraction patterns, which are used in determining the atomic structure. Lastly, the symmetry influences the crystal growths, habits, and reactivity, adding an application of material synthesis and pharmaceuticals. Overall, points groups are essential in predicting and explaining the crystal's properties and application. And let's consider the crystal, the structure itself. It begins with the two square pyramids joints at their bases, forming a octahedron-like shape with eight triangular faces. Next, we make symmetrical cuts from the tops and bottoms, adding two new square faces. These modifications preserve certain symmetries while removing others, giving us a structure with eight triangular side faces and two square faces on the top and bottom. Actually, it's eight modified, and its shape changes to the trapezoidal shape. Eight trapezoidal shapes and the two square faces on top and bottom. Now, looking at the final structure, we can identify key symmetry elements that suggest a specific point group. First, we have a fourfold rotational axis along the vertical axis, meaning the structure looks identical after a 90-degree rotation. Additionally, it also having a horizontal mirror plane, and it's also having a pair of vertical mirror planes which is dividing the shape symmetrically. With this combination of fourfold axis and multiple mirror planes, the structure fits the 4 by MMM point group. In summary, by analyzing the symmetry elements in this modified octahedron, we confirmed it belongs to the 4 by MMM point group, which is characteristics of the crystal in the tetragonal system. This symmetry gives the insight into the structure, physical properties, and potential applications. Thank you for listening. Thank you very much. Hello everyone, myself Ankur Tawar. I will be presenting how to make crystal structures with the help of Vesta program. So I will make a new structure for you, and here we will make a calcium telluride structure. I will name it. Then click on the unit cell button, and I will select the cubic as a system, and the space group I will choose as FM3, which is FCC. So I will add the lattice parameter A, which is equal to 6.356, and click on the OK button. So here we are getting a cube unit cell. So then we will add the ions to this lattice and click on the added data, and then I'll select the structure parameters. So then here a dialog box appear. I'll click on the new button, in this new button, and then I can add the symbol to it. Symbol is first will be the calcium, which will form the FCC ion lattice. Label it, charge on the calcium is +2, and fractional coordinates is 0, 0, 0. So it will form the FCC lattice with the help of translational symmetry, and I will click on the apply button. So as you can see that the calcium ions are on the every corner as well as on the faces of the cube. Then I will add the tellurides ions. Click on the new button. Here this is tellurium, and I will name it. The charge on the tellurium is -2, and as we can know that this calcium telluride is forming a rock salt structure, so it will occupy all the octahedral voids. So I will add at the cent I will add 0.5, 0.5 and 0.5 to the coordinates of the to the telluride ion. Then I will click on the apply button. Now you can see that this lattice, all the corners as well as faces are occupied with the calcium, and the edges and the center is occupied with the anion, which is tellurium ions. So now we can add the bonds to it. Click on the control B, and now click on the new button, the tellurium, and we will give some arbitrary maximum length. Let us choose 5 and apply, and we can choose that do not search atoms beyond the boundary option. Click here and apply. So now you can see that this is our calcium telluride structure, which is a rock salt structure. So I can also give the names to it as per a convenience. So this is how we can use the Vesta software to make crystal structures. We can also make fluoride, anti-fluoride, other type of structure, VCC, FCC and HCP. So other are I have made the gallium phosphide already. Here this is the zinc blend structure. In this, the gallium is occupying the corners as well as the faces. So gallium is making an FCC lattice, and the phosphide ions, they are occupying the tetrahedral voids. These tetrahedral voids are means half of the voids are occupied, and the other half other voids are empty. So this is the gallium phosphide structure, and now I will let you know that this is the anti-fluoride structure. This is a K2O structure. In this all the oxygen are at the corners and the faces of the cube, and the potassium ion, they are occupying all the tetrahedral voids. So this is the anti-fluoride structure in which anions is forming FCC and cations are occupying tetrahedral voids. Similarly, I can also show the cerium oxide, which is a fluoride structure. Fluoride. Now you can see that the cerium, which is a cation, is occupying the corners as well as the faces. So this is forming FCC lattice, and this this is red ones are the actually oxygen atoms. So this oxygen, these oxygen atoms are occupying all the tetrahedral voids. So this is the fluoride structure of the cerium oxide. Now I will show you the gold zinc structure. Now this is the actually primitive structure in which the golds are occupying the corners as well, and zinc is sitting at the center. So this gold zinc structure is also very helpful, and means means all type of structures we can make with the help of Vesta. Thank you. X-ray are the type of electromagnetic radiation with the wavelengths shorter than those of UV light. They have various applications such as medical imaging, industrial inspection, and scientific research. The X-ray are the form of electromagnetic radiation that occupy a unique position in electromagnetic spectrum. This lying in the beyond the visible light and the radio waves. This is characterized by the high energy and short wavelength. X-ray possesses the ability to penetrate through the materials that are opaque to visible light, such as soft tissues and walls. So this penetrating power is very critical feature of the X-ray, invaluable in medical imaging, enabling the healthcare professionals to visualize the internal structures that diagnose the conditions without invasive procedures. The capacity to differentiate the different type of tissues materials is essential in radiology. Accurate imaging is very crucial in effective treatment and patient care. So X-rays are very important tool, very powerful tool in the medical applications and also in the industrial uses as well. So it's demonstrating a significant role in the scientific technology. So production of X-ray involves a series of atomic interaction initiated by the high electron beam directed at a metal target. When these energetic electrons, when they collide with the atoms of the target material, they impart the kinetic energy to the target atoms. So their interaction often led to the inner shell ionization. Their incoming electrons displaces the electron from the inner shell of the atoms. This will create vacancies in the inner shells. So this vacancy create a very unstable conditions in the atom. To restore this stability, the electron from higher level within the atom will drop down to the inner level to fill these vacancies. During this transition, the energy difference between their higher and lower energy levels is released. So this energy release is in the form of X-rays. This process this not only highlights the relationship between the energy transfer and atomic structure, it's also underpin fundamental mechanism through of the X-ray imaging and other applications which are harnessing the power of X-ray as penetrating power of these high energy photons. X-ray features characteristics lines. These are the lines X-ray that indicates the specific electron transitions within the atom. K alpha line results from the electrons moving from the L shell to the K shell, producing high energy X-ray. K beta line occurs when the electron transition from M to K shell, resulting in higher energy. And L alpha line is generated in transition from M to L shell electron. This yields low energy X-rays. These lines are very essential and identifying the analyzing the elemental composition in various material. The X-ray absorption and attenuation refers to reduction in X-ray intensity as they pass through the material due to the processes like absorption and scattering. As X-ray interact with the matter, their intensity diminishes, which is influenced significantly by the material's density and atomic number. The denser materials and higher atomic number tends to absorb the X-ray more effectively. Additionally, the attenuation of X-ray is energy dependent, meaning that attenuation coefficient varies with the energy of X-ray. Consequently, the different X-ray penetrates material to varying depth, means at a very different depths, allowing a very selective imaging of the and the analysis based on the energy levels. This is very crucial in the medical imaging, as we have talked earlier. This X-ray plays a very vital role in imaging. They are crucial in diagnosing, monitoring, We can detect the bone fractures with the help of X-ray, tumors with the help of X-ray, pneumonia, and providing. Uh, Let me go back. So this is the synchrotron radiation. Uh, Let us talk about this synchrotron radiation. This is a very highly intense and bright form of electromagnetic radiation produced when the charged particles, such as electrons, were accelerated to near speed of the light in the synchrotron radiation. This radiation spans a broad spectrum of wavelengths, ranging from the infrared to X-rays, making it a versatile tool for the variety of scientific applications. Researchers utilize this synchrotron radiation in a field such as the medical science, chemistry, biology, medicine, where its high density and wide spectral range allows for advanced imaging, detailed structure analysis, and probing of material properties of atomic and molecular levels. This capability significantly enhances our understanding of complex systems, and we get facilitates through big breakthroughs in various scientific disciplines. In conclusion, ongoing advancement in the X-ray technologies provides a very unlock new applications and enhance capabilities very in various fields. This X-ray remains the vital in scientific research, and it offers deep insights in fundamental properties of matter, driving the discoveries that expands the understanding of natural world. In healthcare, these X-rays are very indispensable in imaging, in early detection, in development of medical treatments. So these applications in industrial setting continues to grow, ensuring the quality control, safety, efficiency in manufacturing of processes. As the research and technology evolve, this future of X-ray applications is poised to revolutionize the multiple disciplines, making it a significant contributions to science and society as well. So, thank you, everyone.